Welcome, colleagues, to this explainer. Look, as oncologists, we've all been there, right? We're all too familiar with the absolute frustration of monotherapy. You target a specific mutation, you get that initial, hopeful tumor regression, and then, almost inevitably, the microenvironment adapts. The tumor evades, resistance develops. It's an exhausting cycle. But today, we're going to look at a definitive, mathematically and biologically backed resolution to this exact problem for IDH1 mutant tumors. We're stepping way beyond the single pathway approach. Instead, we're exploring a dual pathway pincer movement. Basically, it's a combined therapeutic strategy designed to trap the tumor from the inside and the out, literally preventing its survival.
Okay, so here is our roadmap for today. We'll start with the IDH1 R32H target, move into Avonax and extrinsic immune activation, then break down the intrinsic apoptotic thresholds. After that, we'll combine it all into the therapy pincer and finish up with how this prevents monotherapy resistance. Let's dive right in.
Section 1. The IDH1 132H target. Let's start by looking at the sheer promise of the Avonax neoantigen vaccine pipeline, specifically for grade 2 and 3 gliomas.
Now, what's really fascinating about the data generated by this scoring architecture is just its sheer precision. Our top candidate is an IDH1 R132H 9-mer, and it pulled a highly solid 6.34 out of 10, but I want you to focus specifically on the DAI right there, the differential agonism index. It's sitting at an incredibly high 0.829. To put that into clinical perspective, this mutant peptide binds roughly 10 times stronger than the wild type. 10 times! Add to that a clonality score of 0.729, which tells us this mutation is present in about 73% of the tumor cells. So we've got a highly prevalent, distinct target.
As the source analysis perfectly sums it up, this high DAI is basically the holy grail for a vaccine candidate. Finding this exact 9-mer sequence completely grounds our approach in rigorous bioinformatics. Because the immune system can so clearly, undeniably distinguish this tumor from self, we have the foundational requirement for safe, tumor-specific immunity, and we get that without the catastrophic risks of autoimmune toxicity. We have our target for sure.
Moving right along to Section 2, Novavax and extrinsic immune activation. Let's talk about the exact mechanism of action here.
At its core, the Avonax vaccine is brilliantly designed to train effector T cells to recognize our IDH1 9-mer right on the surface of the tumor cells. Once they recognize it, these T cells go on the attack. They deliver an external death signal directly to the tumor via perforin and granzyme B. This immediately triggers the extrinsic apoptosis pathway, specifically driven by caspase 8. Basically, we are knocking incredibly loudly on the tumor cell's front door.
But here's where we always hit the wall in the clinic, right? The crucial complication is that despite initiating this extrinsic attack, these tumors are exceptionally good at surviving it. They develop microenvironment resistance. The caspase 8 cascade might be initiated by our T cells, sure, but the cancer cells actively suppress it from the inside out. They often do this by sequestering cytochrome C, using BCL2 family proteins. The signal gets sent, but the actual execution gets halted. This, colleagues, is the very definition of monotherapy resistance.
Which brings us to Section 3, intrinsic apoptotic thresholds. To beat this resistance, we have to look away from the immune system for just a second.
Let's look at the apoptotic decision surface. In the mathematical models analyzing cellular death, 0.5 or 50% activation is the definitive decision boundary. Now look at this comparison. It's actually wild. We contrast an IDH1 cancer cell against an Alzheimer's neuron. The Alzheimer's neuron is actively dying. It's at an 86.3% caspase activation rate. But look at our cancer cell. It sits at a 51.9% activation rate. It is surviving, yeah, but just barely. Just a hair above that 50% threshold. Visually, this is the absolute proof of why the cancer signal needs an artificial boost.
We actually call this the subthreshold priming state. Our cancer cell has a baseline intrinsic death signal of 0.015, which translates through the mathematical sigmoid function to that 51.9% activation we just saw. Mathematically speaking, this cell is already committed to apoptosis. But biologically, it manages to survive by desperately sequestering cytochrome C. It is literally hovering on a biological knife edge, just barely avoiding its own execution.
And this just brilliantly illustrates the dynamic range of apoptosis. You see, the cascade functions with an amplification factor of 5. This means that a mere 20% initial oxidative stress is enough to push the activation well past the threshold to 0.731 at caspase 8. That makes it a totally irreversible cascade.
leading straight to the caspase-3 executioner phase. Cells with any significant oxidative stress are already internally primed to die. They just need to be pushed over the edge.
Okay, Section 4, the combined therapy Pincer. This is the climax of our analysis and the dual pathway breakthrough we've been building toward.
When we juxtapose these two mechanisms side by side, the strategy becomes incredibly, undeniably clear. On one side, we deploy a Novavax. This trains the immune system to target surface antigens, driving the extrinsic pathway via caspase-8. On the flip side, we administer pro-oxidant therapies. This targets the tumor's intracellular thresholds, driving the intrinsic mitochondrial pathway via caspases 9 and 3. By synchronizing this two-front attack, we don't just fight the tumor, we mathematically corner it.
And let's see how this builds specifically on the biology of IDH1 tumors. IDH1 mutations inherently reduce a cell's production of NADPH. Because of this, these specific tumors suffer from a much higher baseline of oxidative stress. They are already struggling hard to buffer their own catastrophic internal environment. Therefore, they sit much closer to that intrinsic death threshold than wild-type cancers. This renders them uniquely, highly susceptible to pro-oxidant nudges.
Colleagues, 0.085. That is literally all it takes, because the IDH1 cancer cell is already hovering at a 0.015 signal, just shy of the execution threshold. A mere plus 0.085 increase in their apoptotic signal is all it takes to push this tumor from a state of survival into total, irreversible systemic collapse. A moderate, low-dose pro-oxidant therapy is perfectly capable of delivering this exact therapeutic nudge.
Finally, Section 5, preventing monotherapy resistance. Let's talk about how this translates to the clinic. The absolute brilliance of this Pincer movement is that dual activation traps the tumor in an impossible biological paradox. Look, a cancer cell has finite metabolic resources, right? It simply cannot simultaneously mutate its surface antigens to hide from a Novavax-trained T cells while concurrently expending the massive amount of energy required to buffer its internal pro-oxidant-induced oxidative stress. It just can't do both. Deploying a Novavax externally while administering a pro-oxidant internally definitively prevents evasion.
So I want to leave you with this final, critical thought. We have the bioinformatics mapping the optimal extrinsic target. We have the mathematical models actually proving the vulnerability of their intrinsic threshold. If we have the capability to trap IDH1 tumors from the inside and the out, simultaneously, mathematically forcing their apoptosis, why would we ever settle for monotherapy again? The data clearly points toward integrating a Novavax with pro-oxidant treatments in our future clinical protocols. Thank you so much for your time today, colleagues. Let's go change the paradigm.